So I'm talking about what I was doing with Josh. I think here I was missing IIS and ownership from the University of Roma. So it's a work the last year, so it's about algebraic proof complexity of tensor isomorphism. So let me explain you. So first of all, I'm moving in polynomial calculus. So we already have seen the definition of the system. So I can quickly skip this thing here. Just let me just warn that I'm not giving axioms for the variables. So the usual axiom that, for example, the twin axioms that we have in PCR. So here I'm moving in PC because we are only looking at the degree of refuting set of unsatisfiable polynomials. And moreover, we also don't have this, or we will have when it is necessary. So axioms forcing to 0, 1, because actually we are looking at set of polynomials. We are not looking at things encoding from some Boolean form. Okay, just say that. So let me, okay, just some easy question we started from. So essentially, we started from the question about understanding if sort of question similar to the one that Paul was making yesterday evening. So understanding if we can prove that matrix multiplication using some tools, for example, for Grobner basis reasoning, we could be able to prove some limitation on this algorithm, and this limitation should take the form of proving some degree lower bounds in a polynomial calculus. So the first easy question where we were moving from was that we are considering a set of polynomials encoding this simple principle that if you are multiplying two matrices, one of n times n and the other r times n, then 0, 1, we can say here, they are not, they cannot, as long as r is strictly smaller than n, we cannot have the identity matrix. And we were trying to say that, okay, can we prove some degree lower bounds? For example, r is required as a degree for this. This was a starting question. In fact, we can prove some result of this form. I will tell you it's not difficult at the end, but one thing that we were considering after this was moving on some generalization of matrices, and this generalization are these tensors. So let me give you some intuition about this tensor so you can understand a bit what we were doing in the work. So a K tensor, it's so you have, for example, K vector space over some field, and then a K tensor is just an element of the K product of this this vector space, which is itself is another vector space of the dimension, the product of this. Okay, so for example, if you are looking at vector space of matrices, and you have one matrix A in this space and another in this space, the product of A, the tensor product of A and B, it is a matrix of this order formed in this way. I mean, just examples. Other examples to understand, to make you understand a bit better the set of polynomials I will introduce you later. So let's say, for example, that EI is the ith standard basis for a vector space U. Then this product here, it's a basis for this vector space, the product of U. And this vector, for example, this tensor here, you can represent it as a three-way array, who's the, in this case, the only non-zero entry is the IGV. So more or less in this way. So that I mean, just to let you understand that essentially we can look at three tensor as three-way arrays. So, okay, we were thinking about what to do with this tensor. So we went to see this isomorphism problem for tensors. When we say that two tensors are isomorphic, so let's say that we have two tensors t and t prime over some vector space of dimension, so three formed by the product of three vector space. We will always move in this three product of vector space. I will explain you why. And we can say that T and T prime are isomorphic if they can be transformed one into the other by some invertible linear map. For example, a linear change of basis. Okay. Let's see an example. So, and of course, an invertible linear map, it is a matrix. It's a square matrix. It can be represented as a square matrix. So let me show you an example. For example, if we look at two tensors, so two tensors are in fact matrices. And let's say that we have A, B, two tensors in M, the space of M times M matrices. So they are isomorphic if we can find the two invertible matrices X and Y in the space of M times M invertible matrices, such that A, it is X times B times Y. In other words, you can say that the entries of the matrix A, calling here small a, I prime, J prime, are obtained by elements of this, here in this form. It's just a matter of simple definition. So if you get this now, then you can get the same things for three tensors. So in three tensors is the same. We have three tensors, T and T prime, in the product space of U times V times W, whatever. And they are isomorphic if we can find three invertible linear maps, X, Y, and Z, such that T prime, it is equal this object here. And this object here, if you just develop this 1 second, you will see that it's giving this equation or this set of polynomials indeed, because this is the set. Okay, so we also consider a definition of tensor rank. Sorry, so the rank of a tensor, it is the minimal R, such that the tensor can be expressed as the sum of R vectors. For example, vectors in the basis. Here you have an example of two vectors, one of rank 3. See, it's expressible by the sum of three product of vectors in the basis. And here you have an example of a tensor of the diamond rank. Okay. So why we were considering tensors? Well, first of all, and what is the importance of tensors? So tensors are appearing in the hardness condition for post-quantum cryptography assumptions, which are quite recent. At the moment, we already know some concrete example of digital signatures and identification schemes that are using such assumptions based on tensor isomorphism. So it happens that, well, this is seen, we don't know precisely, that algorithm primitives based on Grobnin basis method seem to fail at solving large instances of tensor isomorphism, complete problems. So here I was mentioning these complete problems, TI complete problems. Why? Because in fact, Grochov and some of his collaborators were recently or in the last years proving some result about to understand how tensor isomorphism is behaving with respect or is capturing other isomorphism problems. For example, there are several reductions between TI and other algebraic isomorphism problem. Graph isomorphism reduced to tensor isomorphism, and moreover, K tensor isomorphism is equivalent to 3 tensor isomorphism when k is greater than 3 for k constant. And this is the reason why we are staying with this. And so motivation for proving, so what we were doing actually, it is try to understand the best of our possibilities, the degree lower bounds for the polynomials coming from the tensor isomorphism. So given two tensors that are not isomorphic, we want to understand what is the degree of the polynomials capturing the isomorphism of these two tensor in the polynomial calculus. So motivation for this can come from, for example, try to understand if tensor isomorphism instances that are hard for such solver based on algebraic methods as Grobner basis. This is important if we want to use as hardness assumption, this tensor isomorphism problem. And yeah, and that is essentially the same result. Okay.
So can I ask? So if you just do, forget about just to understand for matrices, right? Let's say square matrices. Is it so the question whether these two are isomorphic, is that basically saying that they have the same number of blocks in their Jordan decomposition, or? I mean the blocks.
I think so. I think it's the same question. Yes.
What is the complexity of tensor isomorphism in terms of conditions on NP versus P?
On condition on NP?
I mean, it's much hard. It's conjectured to be much harder.
No, you write down the matrix explicitly.
So how come it's
Oh,
how come it's based off of post quantum?
Well, I don't know this option. I don't know.
Unless I remember, because I'm sure is if you allow acting with two different matrices, that should be clear that every two matrices of the same range is isomorphic.
yeah, it doesn't require that X and Y are, it doesn't require us to change a basis or any of that sort of stuff, because they could be arbitrary.
But let me see. Let's see where we are, what we are doing. So, okay, some other motivation coming from the fact that no, these are not motivation. These are motivation for some other result that complements in our in this work about the inversion matrix inversion principle that was considered by and some work. For example, in some old work about by Microsoft and Oberwolfach, they were proving that this so encoding on this tautology over 0,1, it's alpha bounded at 3. So what we are doing, it's so we are going to understand this in polynomial calculus. These are side results, however. I will explain you the connection with the tensor. So so essentially we consider these polynomials here. It's explained to you before. For two tensor T in this order here, and of course we have to force the invertibility of the linear maps of X, Y, and Z. So then what we do, it is adding this equation to the set of polynomials. So considering also these polynomials here. So these are set of polynomials encoding this here, where this X prime here are essentially new variables. So we are this is done to keep the degree bounded of all the initial polynomials, because otherwise the degree would have been already big. So then we introduce some new variables x1, x prime, which are related with the x, and essentially are related through this axiom. So more or less like you use twin variables in polynomials. Okay, let's see what are the results that we have. So we have three contributions essentially. So first of all, we found that there are instances of the three tensor isomorphism problem that require PC degree omega of n. So we proved this this result in two ways. So in one way we use a reduction to prove PC proof of the graph isomorphism, and where a degree lower bound was proved over any field by this Berkholz Grohe. And also we get a slightly worse degree lower bound in PC, but this time using a reduction from a result of Elivel, Sassoon, and Russell in Pagliazzo, 99, from the degree of random formulas of three exon formulas over field with characteristic different from two. So this is also propagated to power. So this is the first contribution that we have. So what kind of reduction we are using here? So so we are using this concept of reduction that was introduced for PC, so to keep the PC, the degree in polynomial calculus refutation bounded. So let's say that we have two polynomials, two family of polynomials P and Q, polynomials, that you have to think as low degree polynomials. And then you say that P is D1, D2 reducible to Q if for all I of in M, you can find another polynomial of small degree D1, such that you can, once you substitute this polynomial here to the y variable in Q, you can derive these new polynomials from the initial P1 using again a small degree proof of degree D2. Okay, so here's that means that small degree proof of Q can go to degree small degree proof of.
So should
You mean
digital?
D2 instead of 2, yeah.
No, sorry, yes.
Yeah,
Thanks.
yeah, yeah.
No, D2. Thanks. I think it was disappearing a D moving some object. Okay, thanks. And okay, I just write this way. So second contribution, it is on the upper bound sides for this tensor isomorphism on the rank. So so what we are proving is that if we are in Nustellensatz, okay, I didn't introduce Nustellensatz, but I think it was introduced before. We can prove Nustellensatz refutation of degree 2 to the R squared for three tensor isomorphism over any field or T prime any. And if we move over a field FQ, then and we add these axioms to prove polynomial calculus, we can go down to the degree Q times R squared for this formula here. So just notice that maybe you are surprised of this 2 to the R2 here, but you have to consider that in its set of polynomials we don't have the Boolean axioms, right? So then the proof are, so the trivial proof are going to the number of variables. Okay, so contribution 3, it's are mainly some observation, but are interesting. Requires this rank principle and the inversion principle, the one that I was mentioning you before. This too requires also degree. This is requiring degree n over 2. So this one is requiring. This set of polynomials is requiring degree r over 2 plus 1, and the second one n over 2 plus 1 over any field. But these are essentially are coming from a reduction to the pigeonhole principle of a result of a degree over bounds given by to refute pigeonholes. Indeed, we are reducing exactly to the form of the pigeonhole principle is using. And yes, one contribution that we have there in the paper that we considered interesting, it's sorry that you cannot see, is that we want to add this rule here. Let me just write here this. We want to consider a polynomial calculus plus this rule. Okay, so what do you mean by this precisely? So here we mean that adding this rule, it's a schema, it's a rule schema. You can substitute the instances of. So here you have polynomials actually, and what you can do is you over some variables, and you can substitute these variables for any polynomial. Okay, so what you want is that essentially you can apply this rule. You can get one polynomial in this set here, as long as among the previous polynomials you were deriving all the polynomials that you have here. And I will tell you in the open problems why we consider interesting this system here. But I can just mention you something quickly. The point is that we were not able to prove the small degree proof for the 3 tensor isomorphism, while for the 2 tensor isomorphism is immediate because it's, I mean, you just have the rule there. And then we don't know. We believe that it might be hard for polynomial calculus plus this rule to derive the 3 tensor isomorphism, but we don't know how to do actually. Okay, so let me just tell you quickly about yes, I was just a second. I was yes, okay. How we were getting our results. So all our results are essentially obtained using reductions. So these are not in general what we are doing. It's using certain modification of the problems, looking at the corresponding computational problems, looking at their reduction there, and transforming these reductions into PC low degree reduction. This is the strategy we are using everywhere for this result. Okay, all these results. So, for example, let's see what we are doing here. So here I told you that we are using graph isomorphism, and essentially we are moving from graph isomorphism to another problem called monomial code equivalence, and then from monomial code equivalence to tensor isomorphism. So this reduction was shown in this paper here. This is a reduction shown by Josh and Chow in 21. And so we can prove that this minimal reduction can rise to small low degree PC reduction. Okay, I just have give you the codification of the graph isomorphism problem to make you understand where we are reducing. So I think that also Albert was explaining this yesterday evening. Essentially, we have two graphs, G and A on n vertices, okay. And then we know that, so we have variables Zi, J that are intended to get one if there is an isomorphism to catch the isomorphism that maps I in J, okay. So, and then what we are doing, we are essentially saying that these variables take value 0, 1. So there is a one, so mapping, so the two set are, so the mapping it's a projective here. And then here we are saying that, so we define that two vertices in the two nodes in the first graph maps into two other nodes into other graph. and we call this a local isomorphism if they have the same node in both sides, if that happen. And if in the first case we have an edge, also in the second case we have an edge, actually, if and if. Okay, and then the answer, so the formula capturing the fact that there is an isomorphism between G and H are these formulas here plus these products here, Zij plus Zi prime J prime, where these pairs form not the local isomorphism. Okay, so I wanted to explain here a bit the polynomial formulation of this monomial, this other problem here, that monomial code equivalence. But let me just tell you, so the main things that we are using here, this monomial, a matrix is a monomial if it is exactly one non-zero entry in each column and one non-zero entry in each row. And so when we are encoding this problem here, we need to force this property here. So we have some other axioms capturing these things. And we have, of course, since we have this variable for the invertibility, then we have to do this for all our variables. Okay, but let me just skip this, otherwise I will be not in time. So the result too is for a reduction to the degree lower bounds for random tree linear equation. So here, so essentially we, from this problem here, random tricks, so tricks or linear equation of this form here, xi, xj, xk equal plus or minus 1. We define two tree tensors, t and t primes, in this way here. The first one, t ijk, it's taking an entry 1 if the corresponding monomial has is present an f or not. And the t prime, it is getting plus 1 or minus 1 if the corresponding equation is getting 1, 1. It's very easy. But I mean, to go from tensor isomorphism to random tree XOR, we have to do a series of reduction. I mean, it's a bit requires some work. This essentially at the very end we have a reduction 12 reduction from tree XOR to this side. And the main point here, it's using some result. At some point we have to use this the fact that this is a random formulas, and we are using a result of Ryan O'Donnell of 13 and other about some fact that the hypergraph coming from a random tree XOR things as a formula has some non-trivial. And in the last things we are using a result of this. So this concludes the result that we have. About open problems here, I think that so prove any lower bound in this system that I was telling you. We tried, but we didn't know how to do. And for example, find instances of the three tensor isomorphism that requires high degree to be proved in polynomial. So another problem which is also interesting. So you might, so from what I said, you might led to think that maybe every reduction, every one reduction that is used can be transformed into PC low degree reduction. That it's not true. And then some reduction that, for example, are used in this paper here, are defined in this paper here. It's not clear that can be mapped into low degree PC reductions. Or at least we didn't have success. And so that's it. Okay. Thanks.
Any questions?
What was the reduction that you used to prove the superlinear or exponential degree lower bound? You said that at the first that you have something that is much higher than the linear degree, PC lower bound, but you said that you've used only reductions. Usually they are linear degree.
What was the rank?
No, I don't understand the question. Sorry. Can you repeat it? So what I say?
The first slide you
I
said
don't
you
have
have,
any explanation.
you have some.
I think it was an upper bound.
Yes, it's an upper bound.
Oh, it was upper.
Yes, it's an upper bound. Yeah, indeed. It's the upper bound on the rank. So so essentially, if you have bounded rank tensors, you can refute in Null-Stellensatz, you can refute the polynomials of three tensor isomorphism using degree 2 to the r square or big O of r square. And in the polynomial calculus, it's q times r square if you are moving in a polynomial calculus over the field fq, adding the axiom. So it's an upper bound.
If you don't have the Boolean axioms, why you can have a lower bound higher than linear? In your lower bounds, do you use the
But I don't have degree lower bounds higher than linear.
Yeah, that's I'm asking. Is it possible?
You are asking why it is impossible.
No, is it possible?
Ah,
Your proofs do not use Boolean axioms,
yes.
so it is possible to get beyond linear degree lower bound.
Certainly some exist. I don't know about for these, but double exponential lower bounds exist for some problems. Yeah.
Well, so you are thinking of, so you are asking if it's possible to get better lower bounds. Of course, from what I understand, it should be possible, but I think that already this lower bounds and lower degree and lower bounds that we have are already sufficient to prove some form of hardness. The problems that we were interested in, so let's say that the three tensor isomorphism were not easy to handle through algorithmic primitives based on program basis. Yeah, of course, you can get that. Yes, so you might. I don't know.
More questions.
So tensors towards the end, this P and T prime that you get from these random tensor formulas. So they are anisomorphic for some obvious reason, or is it?
Sorry.
So the tensors T and T prime towards the end, they are anisomorphic because of some obvious reason, like rank, or is it? Or does it come from the randomness of the three CNET, or?
No, it's not coming from the randomness of the three XOR. It's just coming from three XOR, and the randomness it is used somewhere else in the reduction.
Yes, but is it obvious that they are not isomorphic?
Well, it's easy to prove that. Yes, I was jumping that. Sorry. It's yes, it's not difficult to prove that they are not isomorphic. Yes, it's not a complicated way of mapping the three XOR into two non-isomorphic tensors. No, it's not complicated. Yeah, I just put this. No, this reduction here, it's not. So essentially, you have this is the XOR is satisfiable if there exists a matrix A diagonal with plus or minus one entries, such that this equation must hold. Yeah, I was skipping that, but it's not a difficult thing. So you are relating satisfiability of the XOR equation with this equation here.
Okay.
Okay, good. Let's thank the speaker again.